in the last video, we proved the associative property for vector addition. And I've kept up just part of the proof up here that we had previously, because this is a part that it's very easy to miss, that when you're combining these two vectors, a lot of times people leave out those parentheses, because we're really used to being able to add three numbers together. But the definition of vector addition is for a definition of adding two vectors. So you're adding two numbers, the first component of the first vector to the first component of the second vector, second component of the first vector to the second component of the second vector. Okay, so sometimes people just think I'm picky because I asked for this in painstaking detail, and I can live with that. You can just say, I've got a picky teacher. Okay, but I have my reasons for that. Okay. One is just in an effort to be fair when I'm grading. Because if a student shows 5 steps and another student combines steps and does everything in one step, it's really hard to figure out how to be fair in grading. Because the student who showed 5 steps is being much more detail-oriented, but they have 5 times as many opportunities to make a minor error along the way. The student who's combining 5 steps into one is maybe saying, hey, I really get this, it makes sense to me, but maybe they're just jumping and they're missing all of the details. And it's very hard to be fair. So part of it is actually just a logistical, I want to be fair in my grading. But the other reason is actually that if you do combine steps, if you don't have these parentheses here, you miss the crux of the proof. We're proving something that's pretty basic. We're not proving anything that's mind-blowing and earth-shattering at this point. We're proving that, yeah, I can group things however I want to when I'm adding vectors. Not an earth-shattering result, but here's the crux of the reason. The reason that it works for vectors is because it works for numbers. And if I didn't have these parentheses here, if I just wrote A1 plus B1 plus C1, I'd lose the fact that I'm changing from grouping the A's with the B's to the B's with the C's. And it's because I can do that for real numbers that I can do that with vectors. And a lot of math is built that way. We start with very simple things like numbers. We build more complicated things. Many, but not all, of the properties of numbers get inherited by the properties of vectors, but we have to confirm that they do. Let me just give you one example. With real numbers, I can multiply them. We do not have a vector multiplication. Okay. Vector multiplication, if it were to generalize what we have for real numbers, would be a way of combining two vectors to get another vector. And it would be associative and commutative, and it would distribute over addition and all of these things. We don't have anything like that. But it's easy to assume that we ought to, because hey, we can add, we can subtract, we can multiply by scalars, we must be able to multiply vectors. Well, we can't. Okay. Now, we are going to see in the next 2 sections 2 things that are kind of sort of like multiplication. We're going to call them the dot product and the cross product. But they are not a true generalization of multiplication in the real numbers. One of them, we're going to combine 2 vectors, but we're not going to get a vector. We're going to get a number. Another one, we'll combine 2 vectors, and we'll get a vector, but we're not going to have all of the properties that we usually associate with multiplication. So, not everything that we can do with numbers translates nicely into vectors, and so we do need to stop and verify that we can do that. Okay. So, if I ask for you to do a proof in painstaking detail, what that means is that you don't combine steps and that you provide a reason for each and every step. And basically, if I'm asking you to do a proof in painstaking detail, it will be, at this point, it would be one of the properties of vectors that we have, that we're going over in this section, but it'll be something that's fairly basic, and you're basically just going to the component level. Okay. It is very important that as I worked with this proof, I was working with arbitrary vectors. I didn't just choose 3 vectors, like 1, 2, 3, 4, 5, 6. I'm feeling very, very creative. I could very quickly show that 1, 2, plus 3, 4, plus 5, 6 is the same thing as 1, 2, plus 3, 4, plus 5, 6. Okay? All that would show is that this one equation is true. Because sometimes when you pick specific vectors, you happen to pick vectors that have particular qualities. Okay, you might notice that with these vectors, I don't have any negative numbers. I don't have 0 as a component. None of these vectors is the 0 vector. None of these vectors is a multiple of the other vector. Sometimes these things make a difference. And so when I choose specific vectors, the work that I do is only valid for those specific vectors. For that reason, a proof always needs to be done algebraically. If I'm working with algebra, I can have an arbitrary vector. A1, A2, that's any vector in 2 space. If I try to prove things with a picture, I can't actually do a proof with a picture, because as soon as I draw a vector, I've made a choice. That vector is not the 0 vector, because I drew something with magnitude. Now I could make a different choice. I could choose the 0 vector, but then I've made that specific choice. So it's not possible to do a proof by picture. And at this point, I have to rant against textbooks, because in your homework, you're going to be asked to prove some of these properties geometrically, or to prove them by drawing a picture. Those directions are a lie. You cannot prove things by drawing a picture. What the direction should say is illustrate this property by drawing a picture. But anytime you draw a picture, you're choosing a specific vector. Okay? And once you've chosen a specific vector, you can't say this is going to be true for all vectors, because it might be that this vector has some specific properties, like not being 0 is one obvious one, that make the properties true, but that wouldn't be true if I did have the 0 vector. Okay. So, in the next video, I am going to illustrate the commutative property geometrically, but I do want to emphasize that the directions in the homework, and a lot of textbooks are pretty irresponsible about this, will say prove, and they really should say illustrate. If I ask you to prove something, drawing a picture is not enough. You can have a picture to help you think through things. Pictures can be very, very useful, but pictures always involve specific choices. Proofs always involve arbitrary